Alright, you're live on TikTok.
Yay! Oh yeah, I can see that. Great.
Awesome.
Welcome, welcome to MaTHURSDAY. Got a new setup. Whoop whoop. All right, everybody. Should we start out with 2/5 divided by 1/3?
No more. Here's this for you.
Oh, is that for the screen? Okay, thank y'all.
Alright, I'm gonna go watch downstairs.
Okay. MaTHURSDAY. All right, welcome to MaTHURSDAY, where you can ask me anything. I know we've got some, I don't know, like some quarters are wrapping up around here, at least in the public schools and the private schools too, if you're on a quarterly system. So a lot of people are probably getting close to like maybe having midterms and things like that. So if you have any questions, you're struggling to prepare for a test or something like that, just pop it in the chat there. Or if there's any topics that you are teaching or learning, or maybe your kid's learning about it and you need a little refresher. That's what I'm here for. So you guys can see we have a new setup here. We kind of moved everything around, so I'm getting my dining room back, but we are still sitting at the dining room table. So this table here was actually one of the very first pieces of furniture that I ever bought, was this dining room table. I'm still getting used to the setup, so I'm looking kind of at the monitor right behind. But I will try to keep the eye contact up. All right, so let's jump into it. Like I said, if you have any questions, anything that you're learning about, confused about, anything like that, go ahead and pop it in. Pop it into the story, into the chat. Fraction division story problems. I have some that still aren't getting it. Oof, okay. So fraction division story problems, I'm assuming that's like, what, like 5th grade-ish, right? So let's see if we can find, it's so interesting to me, like when did we start calling them word problems instead of story problems? I don't know. Okay, so let's see. I'm just kind of trying to find. Let's see. Yeah, so I'm thinking that it's like, yeah, 6th. I was thinking it was 5th and 6th grade. Okay. Oh, goodness. All these story problems are a little bit rough with these. Especially when you start kind of going into like, okay, so if we've got this, I mean, if you have a specific story problem in mind, go ahead and let me know, because all these ones that I'm coming across, these all feel like, they don't really make any sense. Especially if you're talking about going through and doing, but let's see, let's do this. Okay, so if we have, let's see, Anne buys 3 Barbie dolls to gift her little cousins. If she uses 2/3 of a roll of gift wrap to pack the dolls, what fraction of the gift wrap does she use to pack each doll? Okay, so if we have 2/3 of a roll of the gift wrap, right? So this total is 2/3 of the whole roll, right? And then, so 2/3 of the whole roll. And then we're going to split it into 3. Okay. Yeah, if you have a specific problem, otherwise, yeah, it's kind of hard. Like, usually what I find is, and if you're bringing me a problem, that would be great. But usually what I find is if you aren't sure, like which one to divide by or which one to divide into and all of that. Sometimes I find, like, especially with kids that are just learning the topic, they'll, if you say, okay, what if this were 2 and this were 6? Like, which one would you divide, right? Which one would you divide by or divide through? Like, all of that kind of stuff. So sometimes, like, sort of just reworking the problem, but with nice, friendly numbers can be really helpful for kids to be able to, like, visualize and, like, make that connection of, like, oh, that's what that means. So sometimes that helps. So if we've got 2/3 of the roll of duct tape, and I'm going to wrap 3 dolls up in it. Right? So I've got, so really, I mean, I'm kind of looking at these thirds, right? So this is 1 doll. So this is 1 Barbie. This is another Barbie. And this is another Barbie. Okay? So when you're looking at this, but see, even that, well, see, like for me, I know they're trying to get you to do like 2/3 divided by 3, but in my mind, this would be like 1/3 of 2/3, because it's what fraction of the gift wrap does she use to pack each doll. So what they're trying to get you to do is 2/3, like 2/3 of the roll divided into 3 sections. Okay, so if you did 2/3 divided by 3, right? If you did 2/3 divided by 3, you would have, it would be like the keep, the change, the flip, right? So it would be 2/3 keep, change, and flip. So there you're back at that like 1/3 of 2/3, which to me is sort of like, okay, well, this is 1/3, this is 1/3, this is 1/3, right? And then so 1/3 of the 2/3 of a roll is going to give you 2/9. Right? So I'm actually using 2/9 of the whole roll, right? So I use 2/9 of the entire roll of wrapping paper to wrap to wrap each individual Barbie. Okay, let me see if I missed. Oh, that's, why is this not working? Not able to scroll back up in the chat. Ooh, factoring of quadratics. I absolutely can. I love factoring quadratics. Hold on, I need to send my tech guy, my husband. Ooh, if you're watching, I can't get the mouse to work. Forgot that, of course, I can't get the mouse to work, so I can't like scroll up in the chat on this monitor.
I don't know if the scroll button's configured. Or I don't know how that works.
Okay. Somebody asked for factoring quadratics. If you were, I know somebody was talking about like the dividing fractions. If that was you, can you, if you found another, if you found an example problem, can you put it in the chat? Because I'm not able to scroll back up in it. And so if I missed it, I apologize. Okay. So factoring quadratics. I love factoring quadratics. Ooh, but I hated it when I first learned it. Oh, that's the thing, guys, is that sometimes the math just doesn't math until it's ready to. Sometimes that happens. All right, so factoring quadratics. So factoring anything, right? Factoring anything is writing it as a product of its 2 factors. So like 6, if we factor 6, we're going to write it as 2 times 3. That is factoring. So if I have like 8x, right? I've got 8 times x. Now I don't know what x is, so I can't factor it anymore. But then here I can factor this to 2 times 4. And even 4 I can keep going and I can factor it to 2 times 2. So I could rewrite this 8x as 2 times 2 times 2 times x, right? That's called prime factorization. Okay, so that's called prime factorization, and that's what you're going to be looking for. Actually, something that we're going to look for later, but really just factoring quadratics is figuring out what two things am I multiplying together to get this quadratic. And so usually we kind of talk about, well, eventually we'll get to factoring trinomials, but if I have something like 4x squared plus 2x, okay, and if I need to factor it, that means I need to talk about like, okay, how can I rewrite this in a way that allows me to, well, rewrite it in a way that it's a multiplication problem, not this addition problem, right? Because when you're dealing with addition and subtraction, sometimes it can make it a little bit tricky because you've got all these different terms and you have to talk about like terms and things like that. And so it's sort of like adding and subtracting fractions, right? You have to have the common denominator and all of that. You can't just add or subtract anything like willy-nilly, okay? So what you can look at is you can look at 4x squared plus 2x. So what are these both divisible by? So 4x squared is 4 times x times x. And 4 I could even write as 2 times x, right? Right? 2x I can just write as 2 times x. Okay. Now if I look at these, what I'm looking for is a common factor, which is sort of like a common multiple, kind of. Okay? So what I've got here is I've got a 2 in both of them, and I've got an x in both of them. So what I can do is I can take those out, and that becomes my common factor. So I have 2x, and then what goes, so I'm going to have 2x times whatever left in the parentheses. Okay, so what's left behind if I take this 2 and this x is just a 2x from this 4x squared. I divide it by 2x and it becomes 2x. Got a lot of 2's going on. That was probably kind of a bit of a mistake. That's okay. And this 2x, when I take that 2x out because it becomes this, that just leaves me with a positive 1. Okay, now I can check this by going 2x times 2x is 4x squared, right? So I can do a little check. 2x times 2x is 4x squared. 2x times 1 is 2x. That's a little plus. And there we go. So we can check that if I multiply these two things together and like distribute it, it's going to give me what I started with. Easy peasy, right? Okay, so they get more complicated. Of course they do, right? So let's see. All right, so let's do a factoring trinomial. Okay, so tri means 3, right? Trinomial, 3 terms. Okay. Oh, I need to make sure that I've got one that can be factored. Hold on. Stand by. Okay. So if I give you x squared, let's do plus 8x plus 15. Okay. So again, we're going to be looking for like just what do we multiply together to make this. Okay. Trinomials like this are almost always made for or made from two binomials multiplied together. So like if you remember that acronym, that foiling, right? First, outside, inside, last. That's one of those things like I feel like FOIL and Pythagorean theorem are like the two big things that like everybody remembers from school, right? Maybe y equals mx plus b, right? Because anytime I ask a student like, okay, do you know how to graph a line? And they say y equals mx plus b. And I say, yes, but what does that mean? I think that it's those little like nuggets that you just kind of remember from school that like pop into your brain every once in a while, right? Okay, so we've got, so right here, we've got x squared plus 8x plus 15, okay? So we're going to double check none of these are divisible, right? I can't take any common factors out like in the last example we did, right? X squared, the only factors there are x and x. This is 8 times x, and this is 15, 5 times 3. So these don't have any common factors either, okay? Now, this way that we're going to talk about is going to work as long as this coefficient is 1. Okay, if this coefficient is not 1, then that gets not a little bit tricky, but a little more involved. Okay, so there's a few more moving pieces. Because with these, a lot of times what you can do, once you pick up on the pattern, remember math is all patterns, right? But once you pick up on the pattern, you'll be able to do these very quickly. So what we're looking at is, well, let's look at this. I want to look at this sort of in a backwards way. Okay. So what I said before, so we'll come back to that one. All right. Okay. So we're going to look at, like I said, a trinomial in that form, that x squared plus 8x plus 15, really sort of comes from multiplying something like this, x plus 2 times x plus 3. Okay, so multiplying these together, this is where that acronym, remember, FOIL comes from, right? So FOIL is an easy way to remember how to multiply these things together. Okay, so this is one of the biggest things that you need to know and understand how to do to be successful in Algebra 2, right? Is being able to multiply binomials, multiply polynomials, and factor, okay? So factoring is one of the biggest things that you need to understand in order to be successful in these upper level math classes. It's huge, it's big. Okay, so in order to understand how to undo it, we have to understand how to do it. So first, the f is the first term in each of these binomials. We multiply those together. So x times x is going to give me x squared. O stands for outside. It's the outside term. So x and 3. So since this 3 is positive, this is going to be plus 3x. I stands for inside. 2 times x. So that's plus 2x. And then L stands for last, which is the last terms in each of those. So it's plus 6. Combine like terms, and I get x squared plus 5x plus 6. Okay, so that's where this comes from. That's where these trinomials come from. Now, if you look back at the pattern, right, this number here, this 6 on the end, okay, where did that come from? If we look back up here, and we look back up here, right? It was from the last two terms being multiplied together. So it was 2 times 3. Gave me 6. 6. Okay? The middle term, this 5, came from 3 plus 2. Or 2 plus 3, right? Either way. But it came from these two numbers being added together. So this number here, this 5 in the middle, is from... we add those two numbers, a plus b. Okay, this number here is where we multiply them together. Okay, and it's always going to be this way. Okay, these are going to be where you add them together. This is going to be where you multiply them together. Now, like I said, if it's negative, if this value is right, if this value is 1, like, or if this value is greater than 1, it can get a little bit dicey, but it's not going to be too overly complicated. Okay. So when we have a trinomial like this one, remember the pattern never changes. The patterns don't change. That's why they're called the patterns. Okay. I wonder where the word pattern did come from, actually. Okay. So x squared plus 8x plus 15. So what we're looking for, remember, the pattern doesn't change. So if I've got x plus something, and x plus something. And I know those two somethings come from these values here. What I am looking for is I am looking for two numbers that multiply to 15 and add to 8. Okay, so they multiply to 15 and they add to 8. So when we're figuring this out, we can go through and kind of sort out like, okay, well, what are my factors of 15? There's not a ton of them, right? 1 and 15, those don't add to 8. 3 and 5. 3 plus 5 is 8. So I know that my two factors are 3 and 5 because 3 plus 5 is 8. 3 times 5 is 15. Okay? So we can check this by foiling, right? X times x is x squared. Outside is 5x. Inside is 3x. And last is 15. Combine those two terms in the middle, and I have x squared plus 8x plus 15, which is the same as this one up here. So that is checked. That is my solution. Okay.
We're getting some questions from YouTube.
Oh, that's exciting. What are the questions on YouTube?
Can you give me, well, it sounds a little sus the way it was asked, but please give me the surface area of a square pyramid with a height of 10 and the width of 12.
Okay, is that the slant height? Or is that the height in the middle of the pyramid?
It says height, so my presumption is the height from the base of the pyramid, of the square pyramid.
Okay, so we're finding surface area. Okay, so then it's a square-based pyramid.
Yes.
It's gonna look something like that. Okay, so then it's gonna be there, and there, and there. Lovely. Okay. All right. So then, what were the dimensions? That's a bloopy
10
pyramid.
high from the base, and then 12 along the base.
Oh no! Ah! This marker is dead. Okay. 12. Ooh, that one you can't see. Okay, 12 for the base, and it's a square-based pyramid?
Yes.
Okay, 12 what? Units?
Just 12 units.
Okay. All right, so then the height of the pyramid. So if it's the height of the pyramid, that is different than the slant height. And the reason that they are different is because, so surface area, if you look at the formulas for surface area, holy smokes, they are intense, okay? But ultimately, all you have to remember is that the surface area is just the area of all the surfaces, okay? So if you're just gonna be painting this shape or this pyramid, right, it's like, how much area would I need to cover with that paint, right? So with like the square footage and stuff like that. So if we break this down into thinking about what are each of the sides going to look like, right? That means we're going to have a square, which is the base, right? And that's 12 by 12. Great, we can find the area of that, right? And then you're gonna add 4, we have 1, 2, 3, 4 sides of the pyramid. So 4 triangles that have 12 on the base, right? Because it's gonna line up with the sides of the square. But then the question becomes, if it's the slant height is 10, then that would mean that this side right here is 10. Okay. If it's that the height of the pyramid is 10, then it's a little bit different because we would actually need to do a little bit of Pythagorean theorem to get the height of the triangle itself. So let's just, for now, unless we get a clear answer, 4 times that.
Well, Anna said, yay. So I think it was from the explanation that I gave you. I think the height itself is 10.
The overall height of the pyramid?
Yes.
Okay, not the height of the side?
I think maybe if you could work it both ways, that would be cool too.
Okay, let's start with the easy way, okay? The easy way is if they tell you, so this is called, like I said, it's called slant height. The reason it's different, okay, is that when you have, this is not a triangle, but when you have a side of a pyramid, right? This is kind of hard to show. Okay. I'll just use this thing, whatever this was. I don't even know what this was. Okay. So if you have the side of a pyramid, and if this is 10, right? If this slant height is 10, that's going to be different than if this height were 10. Okay, like the height of the pyramid, because of a right triangle, right? So in a right triangle, you've got that the hypotenuse is going to be across from the 90-degree angle, so it's going to be a little bit longer, okay? So if the pyramid itself the height is 10, then the side of your pyramid is actually going to be more than 10, okay? But we'll go with just the slant height, meaning that like on my pyramid, this distance here is 10, because that makes it a bit easier. Okay, so area of a square is just, or area of a rectangle is base times height, or length times width, however you want to think about it, which is 144. Okay, and then you would add 4 times, the area of a triangle is the base times the height divided in half. Okay, so it's 1/2 of the base times the height. So the base times the height is 120, right? So that would be 120 divided by 2, which is going to give us 60. So we have 4 triangles that are 60 each. Okay, now again, remember we're finding the surface area, so we're just finding the surface of all, or I'm sorry, we're finding the area of all the surfaces and then adding them together. That's what surface area is. Now on the SAT and ACT maybe? SAT I know for sure, they put the little formula sheet, and you should, I'm almost positive that surface area is included, okay? Okay. Oh, okay, so we've got some guesses. Excellent. We got 384, 456, 321. Okay, so we've got 144 plus 4 times 60. Right, so this 4 times 60, 4 times 6 is 24. So I do 24 and add a 0 plus 144. All right, so that is going to give us 384. Okay. That is our total if the slant height is 10, meaning the height from the base of the square to the tip of the triangle, like along the outside of the triangle. That's assuming that the slant height is 10, okay? If the slant height is not 10, now we're looking at the pyramid. Man, if we're going to get into geometry stuff, I got to start bringing home some models that I have.
I'd love it for you to bring home some models.
All right. Okay. Let's see. Pull up my sleeves for this one. Okay. All right, so we've got our square-based pyramid right? But what I'm going to do is I'm going to draw it out. I'm not going to draw it out in that three-dimensional way. What I'm going to do is I'm going to draw it sort of like a cross section.
So she only needed the slant height. So you have completed her request. But if you want to go deep, I think you can go deep.
Okay. So if you have, actually, yeah, I'm going to draw it three-dimensionally because that will actually show what needs to be shown. Okay. So now let's go, it's a little more complicated, square-based pyramid, right? So we've got, these are really hard to draw. I mean, they're really hard to draw when you're being as persnickety as I am about it. Okay. So, because that happens. All right. But there we go. So we've got a square-based pyramid, okay? And our side length is 12, right? And we know that it is square base, so it's 12 by 12, okay? But then the idea is that what if the height of the 10 was not along the side, right? What if it was not along the side, but it was like the actual height of the pyramid itself, okay? So now what we're talking about is the height is from the center of the base up to the top of the pyramid there, kind of like on the inside, okay? So we've got this now to where now we first, because we're still finding surface area, right? We still need to find the surface area of this whole thing, which is just the area of all the surfaces added together. Okay, the base is still going to be a square that is 12 by 12. Okay, that is not changing. So we have our base, which is 12 by 12, and then we're still not, the other things are not changing either. We have 4 times that triangle. But here is the problem, okay? So when we drew it here, right, this triangle was sort of like if we were looking at the side of the pyramid, right? We're looking at it head on and we can see that it's a triangle going up and we see that that's the 10, okay? But now our height of 10 is actually kind of inside the pyramid. So what we're going to be doing is we are going to be looking at the triangle in a slightly different way, sort of like if we cut the triangle in half, or cut the whole pyramid in half, okay? Sort of like a cross section, right? Because if we know that this side is 10, okay? Now what I'm gonna do is this side here, I'm gonna change it. I'm not gonna do pink and red because that's not gonna show up. But if I do this blue side here is actually this blue side here. Okay, that's the height. Okay, so that's the height there. This is the height here. Okay, and since it's halfway, right, we know that that is going to be 6. So this down here is going to be 6. Okay, and what I'm trying to figure out is I am trying to find this here, right? The reason I'm trying to find this here is because it's actually this side right here. Okay. It's a weird way of thinking about it, but this is, you know, I talk about it all the time, like in the years that I taught geometry, it's like, it's a different way, like that spatial reasoning, like being able to kind of visualize these things. And that's why I think, I don't want to say this is a hot take. This is not a hot take, I don't think. But I do think that a lot of spatial awareness and spatial reasoning and things like that have gotten better for a lot of students. It's gotten a bit easier for students to visualize these things because they're all playing Minecraft and Fortnite and all of these like immersive video games. Fortnite is an immersive video game, right? Isn't Fortnite kind of like Minecraft, like 3D and sort of, kind of, Minecraft I think is the main one, is being able to kind of think about these things in those spatial relationships, right? You know, the video games, like I could talk for hours and hours and hours about video games. All in good things, I would say. I would only be saying good things. But so we've got this side. So again, like being able to kind of rotate those things around and really thinking about those side lengths and visualizing all of that is good. So Pythagorean theorem, right? We're going to find this side over here. So Pythagorean theorem is a squared plus b squared equals c squared. Our c squared is always this side, right? It's always our hypotenuse across from the 90-degree angle. So we have 10 squared plus 6 squared equals c squared. So that's 136 equals c squared. I'm going to take a square root. Square root 136. And I get about 11.7, so that's what I can use for that side, right, is 11.7. So I'm going to change this to 11.7. Okay. Now when I calculate with my surface area, okay, now I can change my view to where I've got this base of 12 and this height here of my triangle. So now I'm looking back at like the side, right? And this is 11.7. Okay. So now I've got 144 plus 4 times 1/2 base times height, which is 12 times 11.7, right? So I'm going to do 11.7 times 12 divided by 2 times 4 plus 144 is 424.8. So 424.8. Okay, that's what I got. Let me double check that. So we've got 11.7 times 12 divided by 2 times 4 plus 144. 424.8. Okay, so again, if you get the slant height, great. Okay, it's pretty straightforward, all of that. But if you don't get the slant height and you get the base, or you get the height of the pyramid, your teacher is probably wanting you to use that Pythagorean theorem. Okay, that's a good way to get Pythagorean theorem kind of mixed up in there. All right. Okay, so literal equations was one that I saw that somebody has a test tomorrow. Yikes. So literal equations is one of those things where literal equations are where you have an equation like x plus y divided by b equals c. Right? And they'll say something like solve for x. Okay. One little secret. So again, I kind of talked about this earlier, which was when you would go through and like if you are having a hard time visualizing something, like which one gets divided, which one gets multiplied, all of that, because you're dealing with more complex numbers or something, you can sort of substitute in some whole numbers to just sort of visualize what's going on, right? So I can do that here, right? Especially when you're first learning these, it makes it a little bit easier to visualize. So what if I replaced all of the letters that aren't X with numbers, right? So I would have x plus, let's say, y is 2, b is 3, c is 4. Let's just make it easy on ourselves, right? So x plus 2 over 3 equals 4. Okay? It's the same thing, right? Now let's keep track. How would we solve this? Well, the first thing we would do is we would want to get rid of that fraction, right? So we would multiply both sides by 3. Right? So then we have x plus 2 equals 4 times 3. Right? And then I would subtract 2 from both sides. And I would have x equals 4 times 3 minus 2. Okay, now notice I'm not actually like carrying out, I'm not actually calculating these, right? Because remember, we're just trying to visualize the steps. So what we did first was we multiplied what was on the bottom. Great. And then we subtracted that other number. So it's in reverse order of operations. So now if I transfer this over and look at x plus y over b equals c, and I'm solving for x, okay, first, I don't like how I wrote that. So if I go back to the original with x plus y over b equals c, first thing I'm going to do is the same idea. I'm going to multiply by what's on the bottom. Okay, so now I have x plus y equals, we usually write things in alphabetical order, so I'm just going to do bc. Okay, and now I subtract y from both sides, and I have x equals bc minus y. So it's the same concept. It's just not really simplifying anything. It's just rearranging stuff, right? So you want to think about it. Okay, well, how would I get x by itself? And work through that plan, right? So work through the plan and get into like, okay, what I would get rid of the fraction, I would subtract, right? The first thing you're going to do is multiply or divide to simplify things or to get things onto one side or the other. And then you're going to go through and add or subtract, right? So that's what we did here, right? But it really depends on the literal equation itself. But literal equations are just kind of rearranging, and they are good practice for when you have a formula, right? But ultimately what I always tell everybody is when you have a formula, like, or really anything, but if you have the formula, you don't necessarily have to rewrite it in the different format. Like, you can always just plug in what you know and solve for what you don't, right? You can always just do that. Like, you don't necessarily need to rewrite the formula in a certain way, okay?
Can you help with trig?
Mm-hmm.
We have another question from YouTube.
Oh, okay.
Different person, Pie Trader.
Pie Trader, okay.
Says, hi, can you help me solve this problem or how to approach? Let, in parens, -2, 3, end parens, be a point on the terminal side of, I'm not sure if that's 0 or like a Greek
That's theta.
Theta. That's right. Like a way I was like, that's 0. Like,
Yeah.
No. Of theta, find sine, cosine, tangent of theta, use Pythagorean theorem to find r.
Yep.
Trigonometric functions of any angle.
So find just sine, cosine, and tan?
Sine, cosine, and tangent.
Yep, okay. All right, so trigonometry. I really love trig. I really love it a lot. Once you are able to kind of open it up a little bit and it clicks, it's all very much related. Okay, so I'm going to do this problem without using a unit circle, okay? Which, I mean, having it -2, 3 be on the terminal side, you can't really use the unit circle anyway, but I'm not even going to talk about the unit circle unless you need me to, okay? All right, so it says let -2, 3 be the terminal side. So when you're looking at the terminal side of an angle, when you start talking about trig, okay, you start talking about triangles and angles and all these kinds of things on the coordinate plane, okay? So when you've got these numbers, so we've got -2, marker down. Okay.
You lost so many.
I know. All right, so -2, 3. So -2, 3. So it's going to be somewhere up here. Okay, so we're just gonna eyeball it. It's like around there. So the terminal side of an angle means that when you have an angle in the standard position, you've got one of the legs on the x-axis and the other one, it kind of like opens up around. So it's gonna open like that, okay? Unless it's a negative angle, in which case it's gonna go down like that, okay? But like I said, trig is relating all of these different like angles and side measures and the coordinate plane and all of that together. So the terminal side just means that it's the side that's not on the x-axis. Okay, so this point here is -2, 3. Okay. So if this is -2, 3, we want to think about this, right? We've got these values, this -2 and 3. So that means that this side here, this distance here is -2, right? I know that distances can't be negative, but when we're doing trig functions, I'm going to leave the negatives in there because of the coordinates and because it helps me with whether it's a positive or a negative trig function. Just letting you guys know that. Okay, and then up here, this side is +3, okay? And the way that I know that is because of the coordinate right here, -2, 3, okay? So we've got -2 this way and we've got +3 this way. So here we go, okay? Square roots by hand, not with calculator. Oh yeah, that's coming up. Okay, so here we go. So now what we look at here is we've got a right triangle. Now right triangle trig is great. Okay, so what I'm going to do is I'm going to kind of pull that out from the coordinate plane and I'm just going to draw this triangle like this, okay, because sometimes that helps visualize a little bit better. It just helps to make it a little bit more familiar, right? So that's -2 and that's 3 and that's all I really need to know from there. Okay. Now I've got my triangle. Now I need to find my third side. And what do we go back to? Pythagorean theorem. It never goes away. Okay. So my a squared plus b squared equals c squared. So -2 squared is 4. 3 squared is 9. So that means that this is 13 is c squared. So this side here is going to be √13. Okay, so this side here is square root of 13. Now, if it's asking you to find the exact measurement, leave it as square root 13. Now, 13 is a prime number, so it can't be simplified anymore. And we've got tons of videos and stuff on simplifying radicals. But, so for now, we're just going to leave it as √13. Okay, so, oh, one more thing. I do need to go back to this for just a second. Is that when you have drawn this out, this angle here, when you're talking about trig, this is your theta. Okay, that angle that is made with the x-axis is your theta. It's called a reference angle, right? So that's your theta. So it's already set for you. This is theta. Okay. So I need to find sine, cosine, and tangent. Is that right?
Yes.
Okay. So sine theta, think about SOHCAHTOA, right? So sine is opposite over hypotenuse. So the opposite from here is 3. My hypotenuse is √13. I'm going to leave this as it is. Everybody's going to say like, you have to rationalize the denominator. Hot take, you technically don't because that's left over from slide rule days. But I will show you how to rationalize the denominator in a minute. But I'm going to leave it like this just for a second, okay? Cosine of theta is, let's see, so cosine is adjacent, which is -2, over the hypotenuse, which is √13. Okay? And then we have tangent theta, which is opposite over adjacent, which is 3 over negative 2. Okay, so in this case, the cosine and the tangent are going to be negative. Okay, the sine is going to be positive. Okay, so let's talk about rationalizing those denominators. Now again, but that would be the answer to your question. If your teacher doesn't need you to rationalize the denominators, you can be done right here. Like my class, you can be done right here. Okay. So rationalizing the denominator is something that like I said, it's kind of left over from like the slide ruler days, because that was really nearly impossible, or maybe it was impossible. I never use a slide rule. I don't know, but you couldn't do that on a slide rule. So that was like predating calculators. But if I have a number like this, like 3 over root 13, you can't have that radical in the denominator. So what you're going to do is you can always multiply anything by 1 because it's still going to be the same thing, right? That's an identity property. So the identity property, the multiplicative identity property is that if I multiply anything by 1, it's itself, right? It's still the same thing. So if I multiply this by 1, it'd still be 3 over root 13. But I can use that to my advantage because I can multiply anything by a version of 1 that's going to help me. So my version of 1 that's going to help me is multiplying by root 13 over root 13. It's still 1, right? Anything over itself is still 1. So I'm still multiplying this by 1. But what happens is when I multiply root 13 times root 13, it becomes 13. That's not radical anymore, right? And then on top, I get 3 root 13. So now, because I multiplied by 1, it's still itself, right? It's still the same answer, but it just doesn't have that radical in the bottom. So we can do the same thing with cosine, right? We had negative 2 over root 13. So I'm going to multiply by a version of 1 that's going to help me in my cos. So I'm going to multiply by root 13 over root 13. And I'm going to get negative 2 root 13 over 13. Okay. So if your teacher requires you to rationalize the denominator, there you go. Okay. So these, let's see, will those line up? They line up pretty well. There we go. Okay. All right, so yeah, the reason the radical can't be on the bottom, again, it's left over from the slide ruler days, as far as I know, where you really couldn't have that radical in the denominator because you couldn't do that on a slide. You couldn't simplify that or anything. Like I said, in my class, I do not require my students to rationalize the denominator. Because you can type this into a calculator and get an actual value, right? I can type in 3 divided by root 13, and I get 0.832050. So it's not a great decimal, but it's an answer, right? So that's why you just have to rationalize the denominator. That's it.
Christine asked about the square roots by hand.
Square roots by hand. Okay. So yeah, so you said that's a Reddit thing? Square roots by hand?
This was Christine. She DM'd us.
Okay. Yep. Square roots by hand. Okay. So I'm guessing that if you're finding square roots by hand, you can't use a calculator. And actually, when you're simplifying radicals, and somebody else was asking about radicals too. So this goes back to what we were talking about with the prime factorization, right? So we can do, if we have something like 24, okay? So with 24, if we think about everything that's it's divisible by, right? So 24, first thing that jumps out to me is 2 and 12. Okay. For other people, it might be 3 and 8, might be 8 and 3, might be 6 and 4. To me, it's 2 and 12. I don't know. And then 12 can be 2 and 6. And then 6 is 2 and 3, right? So now once we get it down to all prime numbers at the end of these little tree diagrams, that's what's called prime factorization. Okay, so prime factorization, so that means that I can rewrite this as a product of all these prime numbers multiplied together. So 2 times 2 times 2 times 3. Okay. Now the square root of 24, if I take the square root of 24, okay, move over to this one here. Okay. The square root of 24, I could also think about that as the square root of 2 times 2 times 2 times 3. Okay. The square root is just looking at things that you can, like you multiply the same number together twice, right? And you get an answer. So like square root of 9 is 3 because 3 times 3 is 9. So here, the only way that these numbers can get out of this radical sign is if they have a buddy. And their buddy needs to be identical to them. Okay? So looking through here, oh, this 2 and this 2, they can be buddies. So they can come out of the radical sign and they become just a single 2. The radical sign is still there. And we're left with 2 times 3. Okay. Now 2 and 3, they don't have a buddy. So they can't come out of the radical sign. I don't see any other buddies here. So it's going to stay. So this becomes 2 root 6. So the square root of 24, it's not a perfect square, right? A perfect square would mean that everybody can come out of the radical sign. But I can simplify it to 2, that's off the thing. But I can simplify it to 2 root 6. Okay? So the buddies have to be the same number. Okay? You've got to have a buddy to come out from the radical sign. So let's look again. Okay? So we did 24.
And buddies must be the same number.
Buddies must be the same number. Yep. So let's look at 36. Okay, now 36 is a perfect square. Okay, so let's see what happens when we do this to these numbers that are perfect squares. So I'm going to do the same thing, right? So 36, I think of 3 and 12, right? The last time I did this, I didn't do this, but circle the prime numbers as you go. It just makes it a little bit easier. 12, I think 4 and 3. 3 is prime again. 4 can be split into 2 and 2. So there we go, right? So 36 is 2 times 2 times 3 times 3. Okay. So if we're finding the square root of 36, right, the square root of 36, we can write it as the square root of 2 times 2 times 3 times 3. This 2 has a buddy, so they can come out. And the 3's have a buddy, so they can come out also. So once they come out from the radical sign disappears. Once it's empty, it can't stand up, so it just falls over and goes away. So now you're left with this 2 and this 3 because they came out of the radical sign. So 2 times 3, so 6. So 36 is a perfect square because everybody was able to come out from underneath the radical sign. Okay? So the root of 36 is 6. The square root of 36 is 6. Okay? All right, let's look at another one. Now, as you get going on this, you might be able to start kind of doing these in your head, or you'll pick up on the pattern. But if not, you can still do a tree diagram. It's not going to change. It's always going to be there, right? Okay. So we have let's do 48. Okay. So 48, I think 6 and 8. Okay. 6 is 2 and 3. Those are both prime. Okay. 8 is 2 and 4. And then 4 is 2 and 2. Okay. All right. So 48 is 2 times 2 times 2 times 2 times 3, right? 1, 2, 3, 4 times 3. 1, 2, 3, 4, and 3. Okay. So we already know where we're going, right? Square root of 48 is the square root of 2 times 2 times 2 times 2 times 3, right? So we got a bunch of buddies here, right? We've got these 2's are buddies. These 2's are buddies. Now that 3 doesn't have a buddy. Okay, so if we bring that radical down, right, we've got a 2 that comes out. We've got another 2 that comes out, and then that radical sign is still stuck on that 3. So then we have 2 times 2, which is 4, and 4 times the root 3. So that is the root of 48 simplified. Okay. Can I use an odd number? Yeah, so if they don't come out, if they don't have a buddy to come out of the radical symbol, they just stay in there. Okay, and it's helpful to write them in order from least to greatest. I can definitely do an odd number. How about, let's do, I don't know, let's do 45.
And do we have time to do logarithms and natural logarithms?
A little bit, yes. I could do sort of like a basic thing with logs and natural logs. Okay, what did I say, 45? Okay. All right, so 45, we're going to start with our factor tree, right? I always see like 5 and 9. The first thing I see, right? And then 3 and 3. Okay. So we would have, keep it consistent. So 45 is 3 times 3 times 5. Okay. It's always surprising to me when like bigger numbers like 45 only have like 3 prime factors. I don't know, it's always interesting. Okay, so we're looking at the square root of 3 times 5, right? So we only have one buddy set, and that's 3. 3 has a buddy, so the 3 can come out. But then that radical sign moves down, and it keeps the 5 underneath. So then the root of 45 is 3 root 5. Now all of these I've just been working on square roots, but you can do cube roots, 4th root, 5th root. This method still works, right? But like if it were the cube root, you would be looking for not buddies, but trios, right? How many, like, do we have groups of 3 that can come out, right? So things like that, we can do that. Okay, let's do a little bit with logarithms. I know that everybody's been very patient. Okay, so we're looking at natural logs, hold on. Okay, so when you're looking at a logarithm, it does have to do with like the exponents and stuff like that, and the roots and things like that. But basically, like when you're looking at a log itself, So b is the base of the log there. Okay? So with this, right, so you're talking about, I mean, I assume that you guys are talking about natural logs and things like that, right? But so, like, log base, well,
Yes, he said.
like this. Okay. So something like 6 squared equals 36. So the way that you would write this as a log is you would write like log base 6 of 36 is 2. Okay. So meaning like 6 squared is 36. So the log is like what exponent you have to get or what exponent you have to use to make that number. Okay? So when you're doing that, now if you don't have a base there, right, it's like we usually work in like a log base 10 society, right? So tell me a little bit more about what you need beyond understanding just kind of basically like what the log is. I know 1K was the one that was asking about it.
Yeah, 1K was asking about it. Quincy Davis just asked about equations and proofs. I'm not good at that in class, but with trig.
Yeah, proofs are tricky.
A 1K said logs with negative exponents.
Logs with negative exponents. So meaning like your n is negative here, or just kind of negative exponents in
like if
general.
A number to a power has a negative exponent.
Okay, so all right, so 3 to like the negative 2 power, like that. That negative, okay, all that negative does is it drops it down to a denominator. Okay, so 3 to the power of negative 2 would actually be 1/9 because it becomes 1 over 3 squared. Okay, so that negative in that variable, or that negative, sorry, in that exponent drops it down to the bottom to become 1 over 3 squared. Okay, so that's what it is. So that's if the exponent is negative. Now, if it's if the exponent is a fraction, that is going to be a root. So 3 to like the 1/2. I don't know why I erased that, but 3 to the 1/2 power. 3 to the 1/2 power is actually going to be the square root of 3. That's what that becomes. Okay. I don't know if that helps, but I don't know. Okay.
Can you help with Fermat's last theorem, please? That's the unsolvable problem.
What is it?
Fermat's last theorem.
It's the what?
It was like a notoriously unsolved equation for like 70 years or something.
Oh.
Hundreds of years.
Interesting. Why are you?
Layden is being a bit of a sassafras.
Being a bit of a pip? I don't know.
All right. It's past 9. We have a long day tomorrow.
We do. We have a long drive ahead of us. I hope this helped. I feel like the logarithm question kind of fell off, but I don't know. I'm not sure. it's always helpful to have more details, but can you explain log? I just did. So quickly, I can write what I just had. So if you have something like 6 squared equals 36, right, which we know is true, right? So then what you would look at is, the way you would write this is you would have log base 6 of 36 equals 2. So what you're looking for is 6 to what power is 36, and the answer is 2. Right? So logarithms are kind of like you sort of drop this down and bring this one over and move that out. That's the basic, that's like the 30-second elevator pitch of a logarithm. But we will put it on the list for next week, so we'll get more into logarithms next week. And have a wonderful week. Again, if you guys need in-person tutoring, online tutoring, Cameo tutoring, just, click the link, do the stuff, and check out my profile. I do lots and lots of things.
So leave comments and ask questions in the comments.
Please leave comments and ask questions in there. So yeah, let's make math not so scary for everyone involved.